Let's do a problem having to do with radical polymerization. Recall that in a polymerization reaction, there is a monomer, and then the monomer is joined to another monomer in some regular way, and what you end up with is something that's composed of many monomers linked, and that's called a polymer. So in this particular case, the monomer will be this molecule. Do you know what this molecule is called? This is styrene. It's an alkene substituted with a benzene ring with a phenyl group. And what we're going to do with the styrene is we are going to treat it with a little bit of a radical initiator. In this case, we'll just use a peroxide here, which I'll just indicate generically as ROOR. And then we will heat this up a bit. There's just a little bit of this. So you need that to get the process started, but then it's just used one time. Okay? So maybe by analogy to what we looked at in class today, go ahead and see if you can come up with the polymer that is generated, and maybe you can guess what a good name for this polymer would be. Can you guess what the polymer is over here on this side? Poly something? It's polystyrene. And if you take this polymer and you can manipulate it and you can make it into a foam and you can mold that foam and make it into little cups and stuff. So you've probably used at some point in your life a polystyrene coffee cup. I know Starbucks doesn't use polystyrene, and maybe polystyrene food containers have even been banned in New York City, I'm not sure. But if you know those kind of clamshell hamburger containers, those are also made out of polystyrene. Anyway, can you come up with some reasonable way to get to a polymer of styrene? The initiating event is going to be homolytic cleavage of the oxygen-oxygen bond in the initiator. So remember, one electron goes one way, the other electron goes the other way. So that's the initiation step. You get one of those and a second one there when this thing cleaves. And so here is your initiating radical. What do you think this radical would do in terms of reacting with styrene? And a couple things to keep in mind. First of all, the benzene ring of styrene, remember we have a sense that there's a special stability associated with this benzene ring. So the benzene ring remains unaffected in this process, although it does have an influence on the reaction. And then my other recommendation is fill in the hydrogens on the double bond and think about where the initiating radical would add to the double bond to give the better of the two possible resulting carbon radicals. Well, let's fill in the hydrogens. There's a hydrogen here, and a hydrogen here, and a hydrogen there. And so now what we want to do is we want to add this radical to this double bond. Let me number the carbons maybe to help keep track. There's carbon 1, there's carbon 2. We want to add the radical in such a way to get the better possible radical. So what do you think? Should we add RO dot to carbon 1 and leave a dot on carbon 2, or vice versa, add the oxygen dot to carbon 2 and leave a dot on carbon 1? So maybe with that you can push the arrows for the proper choice there. Let me redraw my styrene molecule over here, maybe just to make things a little bit less crowded. There is styrene, and maybe this drawing is indicative of which regioisomeric pathway we're going to take. Here's carbon 1 and here's carbon 2 as I numbered before. And as this picture maybe is oriented to show, the radical is going to add to carbon 1 because I want to end up with the better radical, namely on carbon 2. All right? So the initiating radical, this oxygen makes a new bond to carbon 1 using this electron plus 1 electron from the pi bond. The second pi electron goes to carbon 2. So if you haven't already, please draw the result of that. Here's my initiator. Here's carbon 1. There's carbon 2. Here is the benzene ring of styrene. Let me fill in all the hydrogens here. There are 2 hydrogens at carbon 1. There's 1 hydrogen at carbon 2. And here is my dot. So the next thing I want to ask you is take a look at this radical intermediate and tell me, as far as carbon radicals are concerned, how would you assess the goodness or the energetic favorability or stability of this particular radical? What kind of radical is it? This radical is secondary, to be sure, so it's a secondary radical. But is that all that it has going for it? No, it's also benzylic with respect to the phenyl ring. What does that mean? Well, that means that it's resonance stabilized. So the next job for you here is, can you draw appropriate resonance structures of this benzylic radical to convince your viewer that this really is a resonance stabilized entity? We're going to write resonance structures in the usual way, except we're going to be using these kind of fishhook things. So I can delocalize my dot there, and then I can come here and do that, and then do that. So this just says use one of the 2 electrons from this double bond to make half of a double bond this way. The other half comes from this dot, and then the second electron from this bond goes on to that carbon. So let's keep going here. So there's going to be a dot there. And now maybe I've convinced you. Where else can this dot go? Well, this dot could end up on this carbon, and this dot could end up on this carbon as well. So be sure that you can draw, I won't do it here, but make sure you can draw 2 more resonance structures of this benzylic radical. All right? So a benzylic radical really is a pretty good radical as far as radicals are concerned. Well, now I have this benzylic radical. It does have these other resonance contributors, but most of the dot is localized on carbon 2 because that allows you to preserve the benzene core. And so remember, we're trying to make a polymer. Let's not forget about that. So so far I've consumed 1 molecule of styrene. Presumably, I have a lot more styrene around. So I'll just write styrene in this way. So here is another unit of styrene. Here is your radical. So how would this radical react with styrene? And let's keep our numbers on here. There's carbon 1 of the next styrene molecule. There's carbon 2. What do you think would happen next? This radical should add to styrene, and it should add with the same regioselectivity that we saw before. Namely, the new carbon-carbon bond should be formed between here and here, and that allows you to make a new benzylic radical with 2 units of styrene incorporated. So see if you can draw that product. when you're doing polymerization reactions, it's very helpful to keep the numbers here. So there was carbon 1, there was carbon 2. There's a phenyl group at carbon 2. Then came another carbon 1 from the second molecule of styrene, and another carbon 2 there. There's a hydrogen there. There's a second phenyl group there, and there's a dot there. Okay? And then guess what? You can keep going, right? So you could add to another molecule of styrene, etc. So can you come up with a structure down here that represents the polymer? Maybe let's have it have, I don't know, what happens after you repeat 3 more times so that you would have a total of 5 units of styrene in your growing polymer chain? Can you draw that? Well, down here you would have you would have 1, 2, and then 1, 2, that's the second unit. Then 1, 2, that's the third. I'm going to have to squeeze it in here. 1, 2, that's the fourth. 1, 2, that's the fifth. And then notice, because of the regioselectivity of this process, namely the dot will always add to carbon 1 so as to put the new dot on carbon 2. It's regular, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And the phenyl group is, of course, on 2. So then I can decorate this chain here like this. And then there's my dot over here at the growing end of the chain. And so this could continue a bunch of times. Notice on the very end of your chain, there's an OR group. But because the chain is so long and it only has one end, well, it has an end on the other side as well, right? So at some point, the chain's going to have to terminate in some way. But really, the properties of the polymer are dictated not by what's way on the ends, but the bulk of the polymer, which is really this regular type of structure. Okay? All right. One final question about polystyrene. Are there any stereochemical features associated with polystyrene? If you look at this, don't forget that there's a hydrogen at each of the carbons 2. There are also 2 hydrogens at each of the carbons 1, but let's focus on this. And notice each of these carbons is a possible source of stereochemistry. So you could imagine, for instance, a polymer as shown with all the phenyl groups. Somehow they've been oriented all toward us. You could imagine them alternating forward and back, or some other pattern, or else maybe it's just completely random. So depending on how one polymerizes different monomers, it is sometimes possible to control the stereochemistry. All right? In just polystyrene, regular old polystyrene, the stereochemistry is not controlled, but in some other polymers, it is.